Would a cell phone work in space? What's the difference between an asteroid and a meteorite? And what is the ultimate speed limit you could get by slingshotting around planets? All this and more in this week's Question Show. Welcome to the Question Show. Your questions, my answers. As always, wherever you are across my channel, if a question pops in your brain, just write it down. I'll gather them up and I will answer them here. All right, let's get into the questions. Tiago Tiagat. What would it take to modify a cell phone to make it survive in space long enough to be useful like a CubeSat? So a cell phone would work fairly well in space as is, that you could just take a cell phone, put it into a rocket, fly it into space, and then it would be able to take pictures and attempt to communicate, although, it might be too far from a cell phone signal to be able to actually receive any signal. But there are a couple of problems with having a cell phone in space. And the first problem is that it has a form of cooling that uses the air. So in other words, like when your cell phone gets warm because it's running all of its computing process, it depends on having the air, this ocean of air all around it to cool it back down. So you get this convective cooling because the air is passing over the cell phone. And out in space, you can't use that. You can't use the convection of the air. You can only use the radiation that's coming from the cell phone itself. And so the cell phone would overheat without the ability to radiate away in space. So you would need to add some kind of radiators onto it. And when you look at the International Space Station, it's got a bunch of things that look like solar wings, but they're actually radiators. It has the solar panels, but then it has these additional things that are just to radiate the heat away. And you can imagine if you scaled up your cell phone to that, you can imagine a form of power. Maybe you would put some solar panels on the outside of your cell phone, fly with little solar wings, and it would have some radiators as well that would be getting rid of that heat in some way. And it depends on the spacecraft, right? Like a lot of spacecraft, they can, they're built with a size so that they're able to remove their excess heat as they're generating it at sort of the perfect balance. But a cell phone is just not designed for that. It runs hot and fast. The second problem is that a cell phone is made with sort of very cutting edge technology where you've got, I don't know what the process standard, like 3 nanometers, like the size of the transistors on a cell phone are incredibly small. And one of the big problems that happens with spacecraft is they get hit by cosmic rays, which flip bits. And so a lot of the electronics that are chosen for space missions have been proven over time. They're flight proven, space proven. And in many cases, they're a couple of generations behind the latest models of spacecraft. You might see, like an older ARM chip or an older RISC chip or an older Intel chip that flies on a satellite because it's as fast as it needs to be, but it's also more space hardened to be able to handle cosmic rays striking it, while a cell phone is just really not designed to be bathed in cosmic rays. And so it would work, but the chances of you getting a cosmic ray going through, messing up some of the electronics, either temporarily or permanently, get higher and higher with the complexity. And so it wouldn't be your ideal spacecraft, but it would probably just work. Like if you send it to space, turn it on, you could take a bunch of pictures of Earth and it would be fine until it overheated or the cosmic rays hit it. Now, what's kind of amazing is that there's really a revolution in the size of spacecraft, these things called CubeSats, and they come in these standard units. So a standard CubeSat is called 1U, and that is a 10 centimeter by 10 centimeter by 10 centimeter cube, like about this big. But that's not the smallest standard size that you can get CubeSats. They go down to 0.25U, and so that is 2.5 centimeters by 2.5 centimeters. So that's this tiny little cube that you could theoretically pack filled with electronics, and you could actually fly that to space, and they're designed to work in space, and there's off-the-shelf hardware that you could use to go with this CubeSat, and it's all sort of has been figured out. And so, a cell phone, again, would work, but it wouldn't be your ideal choice. It would be sort of, you'd have to make a lot of modifications. But instead, you can pack into a 0.25U CubeSat package a power system, a camera, communication systems, like all the bits and pieces that you're going to require. And they're relatively inexpensive, super inexpensive to build. And now as launch costs are coming down, they're getting less and less expensive to actually fly. And a lot of the big spacecraft providers, like SpaceX, will provide CubeSat launches where they'll launch close to 100 satellites all at the same time. CubeSats, and they just pack them all together. They're built in this standard format. So you might get one that is, say, 6U, it's like 6 units, and then one that's 2U, and one that's 1U, and then one that's a quarter U, and they pile them all up and they fit them into this, I don't know, like a Tetris container, and they're able to launch them. So instead of trying to send your cell phone to space, come up with an idea that'll fit within a 0.25U CubeSat, and then pay for the launch costs, and you could go to space. Now, I'm sure you've noticed the Stargate planet name that has appeared above my shoulder. And this is a way for you to vote, for you to tell us what you thought was the best question of the week. And we're still sort of catching up from the summer hiatus, so we haven't got the vote tallies in yet. And so we can't tell what was the winning vote from last week, but go ahead and watch the entire video, see what all of the planet names are, and then whatever you thought was the best question, go ahead and put that name into the comments down below. We will celebrate the winner next week. Simon Amazing Clark. Hi Fraser, asteroid versus meteorite. I'm guessing there's a size difference. Can you explain what it is? Cheers. You're close. An asteroid is something that's in space, while a meteorite is something that has struck the Earth. And so if you are walking along the ground and you find a metal rock that came from space, you've got a meteorite on your hands. But before that thing struck the Earth and landed on the ground, it was an asteroid. But there's actually sort of a bit of a break as well. You've got asteroids, which are big, and then meteoroids, which are small and are crunched up pieces that came from asteroids. But there's no clear distinction. Meteoroids are pebble-sized, while asteroids are bigger. And so like we saw recently, an asteroid struck the Earth above the Philippines, exploded in the atmosphere, and it was 1 meter across. And so it's an asteroid before it gets to the Earth. It turns into a meteor as it's passing through the atmosphere, and then it's a meteorite when you find the fragments on the ground. But if it's smaller, pebble-sized out in space, then it's a meteoroid that turns into a meteor that turns into a meteorite, although they never make it into meteorites. I hope that helps. George Spalding 7640. Why is no one talking about what happened to Orion, Meade, and Coronado telescope companies? This is devastating news for the astronomy community. So for those of you who aren't following the story, something happened to Meade telescopes. Now, back in the 80s and 90s, Meade telescopes was the big competitor to Celestron telescopes. In fact, Meade was bigger, and they made a bunch of telescopes. But one of the things that they really competed well with Celestron in was these Schmidt-Cassegrain reflectors. So when you think about the sort of stubby little telescope that comes from Celestron, it's a lot more portable, it's a lot easier to move around, and it's a really sort of nice, perfect size to use as a telescope. And Meade made their version of that telescope in different sizes, 8 inches, 6 inches, 10 inches, 12 inches. And like I wanted a Meade telescope for a long time. I was sort of fine to go either way, like get a Celestron, get a Meade. In the end, I got neither, but they were a great telescope manufacturer. And then there was a bunch of mergers in the telescope industry with Orion and Meade and Coronado. They make a solar telescope that you can look at the sun with. And we got the news on July 14th that they shut the company down, that nobody was coming into work that day. And we don't know what happened. There's a story on Sky and Telescope, and there's a bunch of conversation and discussion forums, but really don't know exactly what happened. So I'm going to recommend that you watch a video from Dylan O'Donnell. He sort of goes into the shipping amounts by the various companies to show when there's maybe a drop off in their production rates and when it looks like the companies were struggling. And we don't really know. Maybe the companies have been acquired now by another company that, who knows what the future is. But clearly something has gone wrong with these companies. And, there are less telescope manufacturers in the industry now. And it's too bad because they were superstars back in the day. And here we are today. So anyway, I don't have any answers for you. Dylan has some answers for you, and we're gonna have to wait and watch and see how it all plays out. But it really is sad. It sucks. Anna Paleorush. Was our sun and solar system formed from a generation 2 star that went supernova? If yes, can we learn something about the star, size, chemical composition, etc. by exploring the solar system? So it's not exactly that cut and dry. There are 3 generations of stars in the universe, and 2 are observed and 1 is theoretical. So here are the observed generations, right? There's the population 1 stars, and that is the sun. The sun is part of the population 1 group. And these are modern stars in that they are filled with a lot of metal that came from the deaths of other stars. And then there are the population 2 stars, and these are metal poor, and they're generally a lot older. And many of them just formed just a few billion years after the universe began, while a star like our sun formed maybe 7 billion years after the beginning of the universe. And then the first generation, although it's called population 3, are the sort of theoretical stars that were made of the primordial hydrogen and helium that's left over from the Big Bang. So you had, in the very beginning, you had only hydrogen and helium and a little bit of heavier elements, and those formed those first stars. Those first stars exploded as supernovae. They polluted the clouds of gas and dust with additional material. That went on to form the population 2 stars. And then through subsequent supernovae, you got the population 1 stars like our sun. And so the problem is that stars are formed from a variety of different raw ingredients. So most of the material that is in the sun is still that primordial hydrogen and helium that is left over the Big Bang, like almost all of it. But then you have trace amounts of other metals. And the sources of those metals come from a variety of places. You've got stars like our sun that are bloating up as red giants, and they're blowing out their outer layers back into space. You've got colliding neutron stars creating kilonovae that are creating a lot of heavier elements that are falling into these stars. And yeah, you've got stars that are much, much larger than the sun going supernovae. And when you think about sort of the time, these are happening at all times. So it really just depends on the amount of metal that was in the star that when it died was able to pollute the next star generation down the road. And so it's not cut and dry. You can't just say, oh, you had the population 3 stars. Man, it's so backwards. I'm going to rant now. Like, should we go just revise the entire process? So it goes population 1, 2, 3 in the order that the stars were formed. Oh man, astronomers are just, there's no way they would be willing to do that. We have to change all the literature. But anyway, so you've got the population 3 stars that are exploding. They are sort of polluting. You're getting the population 2 stars. The population 2 stars are dying and exploding, and you're getting the population 1 stars. But it's just not cut and dry, right? There's just like different events. Like who knows? It could have been hundreds of different stars exploding at different times in the length of the universe to create a star with as much metallicity as our sun has. And it's really just the time in the universe when the star formed. The stars that formed early on in the universe had less metal available to them than the ones that formed now. And if, star formation kept going at the rate that it does in the past, then you'd have stars with incredible amounts of metal into the future. But star formation is winding down in the universe already. And so we're not going to get those subsequent generations where you could really say there's something very different about that metal polluted star. JPBHH, is it possible for something to be double gravitationally lensed? Yes, theoretically, you could have a double gravitational lens where you've got some background object and then you've got a object that is in front of it, some massive galaxy cluster, and it is providing gravitational lensing. And then you've got another object that is in front of that and is providing another gravitational lens. And you've got this sort of twice lensed object. And it would be the most effective natural telescope you could possibly imagine, except for a triply lensed system. But the chances of getting 2 galaxy clusters that are lined up perfectly in that way is just incredibly rare. And we don't know of an example of a doubly lensed object. But there's a sort of a version of that, which is that astronomers measure the path that light takes from really distant objects, and they're able to map out sort of all of the gravitational lensing, the combined gravitational lensing and distortions that happens to that light. Light doesn't take a straight path across billions and billions of light years. It's following this curved, winding path as it's being sort of pushed back and forth by different concentrations of mass and gravity. And so, everything is following this sort of weird twisting path to get to our, us as the final destination. It's just, it's degrees. It's how much is actually happening. And a gravitational lens is sort of a very special, pristine version that gets you this magnification of a background object. Jesse Ray, simple question. What's your favorite thing to observe visually? Currently mine would be globular clusters in my 8-inch Dob. So I think for me, seeing Saturn always just brings so much nostalgia and so much emotion looking through a telescope. It was like, for me, it was this binary event that I looked through a telescope for the first time and I saw Saturn. I saw the rings of the planet. And it was this thing that I had seen pictures of and been fascinated by. But when I actually could see it with my own eyes, you look away from the telescope, you're not seeing Saturn. You look in the telescope, you're looking at Saturn. It's a weird experience. Whenever I would set up my telescope and show people Saturn, and they'd be like, this isn't real. Like, is this a picture? What's going on? No, you, just like Galileo, you are looking through a telescope and you were seeing a planet far away that has rings. Although Galileo thought it had ears. But anyway. So I would say Saturn, and then the moon. I mean, the moon feels like it's bottomless. You can just take your telescope, scan around the moon, and there are so many interesting objects, so many weird features and craters, and especially when it's in a crescent phase and you get these really long shadows and it really shows all of the features on the surface of the moon. It's just so cool, and it's so close, right? It's so much magnified. But then, yeah, I would say globular clusters are this sort of perfect thing to look in a small telescope, because unlike galaxies and nebulae, which are very faint, and if you're doing any visual astronomy, like, the best you're going to do is there is a fuzzy blob in your telescope, and you know in your heart that that's Andromeda, or you know in your heart that that is the Eagle Nebula or whatever. You can't make it out. You can just make out this gray blob where this nebula should be. And you can then refer to pictures from the Hubble Space Telescope. But when you look at a globular cluster, they do look like this little ball of buzzing stars. And it's very much like a small version of what you would see as a big picture from the Hubble Space Telescope. And you get that direct connection. So I agree with you 100% that the globular clusters are one of the most interesting and, most, they really connect you with the real object, unlike galaxies and nebulae. Homu, can you make a 2 AU interferometer by taking data from the same telescope, but 6 months apart? So I'm sure that the recent video that we did on interferometers and like answering every question about interferometers just gave people with more questions. And so you're asking, could you have a telescope in space that is taking an image of the sky from one side of the sun, say at Earth's distance, and then the other side 6 months later, and that gives you a telescope that is 2 astronomical units across, twice the size of the Earth's orbit? And the answer is no. Because you need to record the exact, precise, same data in time. And so what you're saying is, could you do it 6 months apart? You're describing Gaia, the Gaia mission, which is a telescope that is watching the positions of the stars from one side of the Earth's orbit and then the other side of the Earth's orbit, and watching how they kind of blink back and forth as you move around. That tells you the distance to that star. But for you to be able to build an interferometer, you need to be recording the light from the sky in the exact same moment in time. You literally have to be receiving the same wave fronts that are coming off of the star. And so with visible light telescopes, that has to be done in real time. But as the wavelengths get longer, so for example, if you move into infrared, you move into microwave, and eventually if you move into the radio wave spectrum, then the size of the wavelengths are so big that an atomic clock will allow you to just record the time that you recorded your images of the sky. And then you can use, say you have one version of your spacecraft on one side of the sun, and then one version of your spacecraft on the other side of the sun. And as long as you have atomic clocks on board and the wavelengths are wide enough, then you can, after the fact, calculate when these wavelengths were taken, when those wavelengths were taken, and then you can merge them together in computer, and as if you were recording this in real time. And this is what was done with the Event Horizon telescope, which took those amazing pictures of the event horizon around the supermassive black hole at the heart of M87 and at the center of the Milky Way. And what they did was they had radio telescopes around planet Earth, and they all agree, and they all had atomic clocks attached to them. And the appointed time, all of those telescopes started gathering their data locally simultaneously. And they recorded all that data to hard drives, stacks and stacks of hard drives. And then they physically flew those hard drives to one location and then matched up the time codes for all the different telescopes and then used computers to sort of merge all of the signals together. And you got the equivalent of a telescope with the size of planet Earth, as if it was recording the images in real time. But that only works in the radio spectrum. Once you shift into microwaves up into infrared, then you have to start doing this in real time. You have to have your telescopes literally physically linked by a fiber optic cable, and you have to sort of fine tune the two telescopes so that they're perfectly lined up down to the wavelength. When you think about visible light, whatever, it's 500 nanometers. If you're off by a fraction of a fraction of a fraction of a millimeter, then you're not on the same wavefront and you're not able to align your images and you don't get the benefit of the interferometer. So 6 months apart, no, because it needs to be exactly in real time. Ronaldo, why do black holes have different sizes and masses despite all of them having a singularity that is infinitely dense? So we don't actually know what's going on inside the event horizon of a black hole. They call it the singularity, but that's more of a mathematical description of what's going on inside the black hole, that you can treat all of the mass inside the black hole, inside the event horizon, as if it is a infinitely dense point of space that is containing all of the mass of the black hole. And that the sort of ramifications in space is that this creates the event horizon, this region around which defines the speed that you would have to go to be able to escape the grasp of the black hole. That once you are inside the event horizon, you have to be going faster than the speed of light to be able to escape the black hole. Or really specifically, all roads lead to the singularity. That even if you could go faster than the speed of light, you still couldn't escape a black hole, because now really it is sort of the future light cone of everything that is within the event horizon ends at the singularity. But if you are just outside the event horizon, then you can escape out into space as long as you can go the speed of light, or even like a little bit less, depending how far away you are from the event horizon. But we don't know what's inside the event horizon. Like, it could just be that there's, if you could actually pierce down into the event horizon, just below the surface, there is this giant object, the black hole, and it is just right under. And so actually the density of the black hole is the event horizon density divided by the mass. But it could also be that a black hole is significantly smaller. Maybe it's, for every billion light years, it's, this much bigger. Who knows? Or it could be infinitely dense, or it could be getting even denser over time. And we just don't know what that answer is. And so to keep it simple, astronomers, when they run their calculations with black holes, they treat it as if it's infinitely dense at the center of the event horizon. But what it actually is, we don't know. We may never know. No one wants to go inside to check. If you want to support the work we do at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Want the extra parts of the live stream that aren't in this edited version? You can sign up for a special patron-only podcast feed and get the overtime segments, as well as other special behind-the-scenes episodes, including our monthly patron-only question show. Thanks to everyone who has already subscribed, and welcome to our recent newcomers: Sarah Turney, John Heron, Sam Dallas, Jeff McLeod, Justin Adamson, DM Scott, Yusuf Ahmed, C. Story, Stephen Fowler-Munley, Evan Tabor, Nerb Smith, and Douglas Pastorek. Join the club at patreon.com/universetoday. Shadow Mask, should we care that Starliner landed in one piece? I'd like to see what the entry was like. We should absolutely care that Starliner landed in one piece. That's really good news. And that means that now Boeing and NASA can look at the spacecraft as it returned and really try to trace down the problems that it was having when it was flying in space and when it was attached to the space station. Now, a lot of the problems were with a separate part of Starliner that, you know, the boot, the trunk, and that has re-entered the Earth's atmosphere. And so they're going to have to figure out what they can from the capsule itself. But it's way easier to try and sort out and figure out what your problems are if you actually have the hardware for analysis, and the people who built it can look over it and can double check the work and figure out where their problem was. And I mean, I think that there's a lot of people that are wanting Boeing to fail. And I think that that is I don't agree with that perspective at all. I think we want Boeing to succeed. We want there to be multiple ways to get human beings to the International Space Station. We don't want to be completely reliant on one provider. We saw what happened, right? When the space shuttle was decommissioned and there was no other way for NASA, for the Americans to be able to get their astronauts to the International Space Station, they had to rely on the Russians. And it was only when SpaceX finally got Crew Dragon flying that you had some options. There was competition, and NASA was able to then spend money, keep it internally, work with local providers, improve aerospace in the United States. And even sort of more forward thinking, they wanted to have multiple options. They wanted to have Starliner. They wanted to have Crew Dragon. And in fact, you know, probably there will be a human rated version of Dream Chaser eventually. So it's better to have options. It's better to have competition. It's better to have multiple providers who, if one of them struggles, the other one can fill the gaps. If one of them is starting to veer towards overpricing you, you can just shift your business to the other one. Like, if you want a future in space, you want as many different companies as possible to be able to provide these services. So the fact that they got the spacecraft in one piece is great. The fact that now they're going to be able to analyze it, and the race is on. Like, Boeing has got to demonstrate that they can solve these problems, that they can launch humans to space safely, they can bring them back safely, and we'll find out if they're going to have enough time to fulfill their contract to get enough. I think they're supposed to commit, they're supposed to be able to provide 6 Starliners before the end of the mission, and that's 2030. So they've got to be able to launch 1 Starliner a year from now till 2030. So they got the work cut out for them, but I really hope they succeed. And not because I have any special fondness for Boeing, but I just think there should be competition. NASA should have options. We want as many possible choices to get people to space as possible. Always. Alamgir Mia, what is your view on Elon Musk polluting the night sky with Starlink? I've talked about this quite a bit in the past. I am ambivalent about Starlink. So, there's a lot of pros and a lot of cons. On the pro side, you've got satellite access to the entire planet that is being provided by Starlink. And they're rolling this out. I mean, you can go and look at a world map of the places where Starlink is now provides services in, and there's not a lot of countries left who, you would go to and not be able to access Starlink. But the countries that don't have access right now are the kinds of nations that could get a lot of value out of it. You've got nations in Africa, nations in South America, nations in Asia and stuff where infrastructure is very bad, and to be able to get high-speed internet access in the middle of nowhere would be a game changer for a lot of people and help sort of raise people's standards of living and so on. And I think that was the hope. That was the promise that we were really expecting was, okay, we're going to pay this price in our night sky, but the benefit that we're going to get is we're going to get access to the internet around the entire planet, so that you could be in a small village in the middle of Canada, although this does work here, and you can set up a Starlink at the local library and you can provide high-speed internet access to everyone in that village. That is already possible today. That none of the tel companies in Canada would want to run 100 kilometers of fiber optic cable to your town or to your village, but now you can just set up a Starlink and you're good to go. But in other nations, that's not entirely the case. So we're waiting for that promise, and it is moving forward, but we're not there yet. I think once there is global, worldwide access and relatively inexpensive prices for people to use Starlinks when they're in nations that have a lower standard of living, I think that will fulfill on the promise on what it's doing to the night sky. On the flip side, on the night sky, I mean, you can't go outside and watch Starlinks with your unaided eye. They're too faint. And so I think a lot of people were really concerned that we were just going to lose. You would walk outside and you would just see this grid of satellites moving overhead. And that's not the case. They're below what's visible with the unaided eye. But they're very visible in telescopes. And so it's astronomy that is paying the price of being able to, be able to view the night sky, and especially the kinds of astronomy that is looking for asteroids, the ones that are coming from the, you're looking for asteroids that are close to the horizon, near the sun. And that's a time when Starlinks are visible in the sky, when they're being illuminated by the sun, they're close to the horizon, just after sunset, just before sunrise. Those are the times when you really want to have access to a dark night sky. And that's when Starlinks are visible, even with the unaided eye. And pilots see them all the time and think they're looking at UFOs. And I think, a lot of this problem could have been solved just with better communication. That if SpaceX said, we want to build this global satellite constellation, but we want to make it as minimally intrusive to the astronomy community as possible. And what we'll do is make this available to people around the world so they can communicate to the internet. Like, that is really important. And they could have come up with communication systems, ways of coordinating with time, so that you knew that a Starlink, as it was passing overhead, maybe would turn off its transmitters while it's passing over the observatories, or that the observatories would have really accurate, like down to the hundredths of a second timing for when the satellite was going to pass overhead. And then they could just pause their observations for a fraction of a second as the satellite passes overhead and then turn it back on again. And you could remove most of the problem with better communication, but that communication didn't happen. You just got this race to put these satellites in orbit. And now people are having to come up with the legislation after the fact. And so, I think that humanity having access to internet around the planet is critical. I've sure spent a lot of time on the internet all day, and I think everybody wants to spend a lot of time on the internet to just be able to access all of the information that humanity has available. And yet the price we pay is degradation of our astronomy. And that could have been ameliorated by communications, by better plans. But people don't want to sit down and plan and communicate. They just want to move forward. So here we are. And it's not perfect. And I think there's lots of room for improvement, especially for the new groups who are making their own constellations. Communicate, please. Adam Thompson. Hi there. People I've been around have suggested that public funds on space are wasteful. I've had retorts, but I'm curious what your response would be. So there are really kind of two ways that humanity spends its money. I mean, obviously there's lots of different ways, but when you think about it, like, there are the things that we do as we consume. We buy food, we buy gasoline, we buy cigarettes, we spend money on lawn care. There's all this consumption that we make. And then we explore. And there's the amount of money that we spend just on basic science and research, where we are just trying to widen our understanding of every single part of nature, whether it's human biology or whether it's fundamental physics or chemistry, materials science, and astronomy is one of these things. And we don't know. The whole point of basic research is that we have no idea what the benefits are going to be with the money that we invest. And if you knew in advance which things were going to pay off and which things weren't going to pay off, then it wouldn't be exploration. It would be engineering, or it would just be, it would be known bets. And yet here we are in our modern society, and everything has been improved by all of those investments in basic research that were made. We're talking using computers through the internet via airwaves and fiber optic cables and radio transmissions and LCD technology and transistors, and like it just goes on and on and on, right? Thousands and thousands of things that we do to make our lives better today that were at one point just basic research. Nobody knew, like, what happens if you, if you light this on fire? What happens if you remove all the air from that? We don't know. And so always, we have no idea what are going to be, what the benefits are going to be, but we just know that they seem to happen, that as long as we continue to explore, as long as we continue to try to understand nature at its most basic levels, wherever we encounter it, benefits accrue to humanity. And so one good example, like what is a benefit of space, is we realized that major extinction events in the past were caused by asteroids. And we have been able to figure out and plot the trajectories of asteroids thanks to telescopes. And now with the DART mission, we were able to launch a rocket, which is like a whole stack of basic science all in one piece, to an asteroid and strike it and change its trajectory. And so now we have taken what is potentially a catastrophic risk to humanity, and we are making meaningful progress into taking it off the table. That if the dinosaurs had spent time doing basic research into astronomy, maybe they would have stopped that asteroid, but they didn't. They didn't think it was important. And what happened to them? Well, we learned their lesson and said, let's do basic research. And so I think there are arguments to be made about whether these kinds of basic research are more likely to provide benefits than other ones. And so whenever anyone says, like, I don't think we should be spending money on this thing, I say, okay, we'll tell you what, let's just write down all of the things that public money gets spent on. Oh, I don't know, war, military, you could just write down all of these things that public money gets spent on. And just like in general, humanity seems to do better when we try to understand the universe itself, both at the largest scale and at the smallest scale. And that is what has given us all of the benefits that we appreciate today. And so, you can't know which science isn't going to pan out. You just have to explore. Robert Candelario. Do you believe the space race can be reignited between us and China instead of Russia? Maybe NASA can receive more money for space exploration, especially to explore Europa. I don't think that you want to really describe things in terms of a space race. I think that competition and national pride, that's one way to help inspire you to move forward. But it feels like it's a very dirty fuel compared to the other kinds of possible inspiration to get better at space exploration. And so when you think back to the Cold War, when it was the Soviets versus the Americans, and they were both on a race to launch satellites. I mean, yeah, it was an amazing accomplishment when the Soviets launched Sputnik and you had this beep, beep, beep as this satellite was orbiting around the Earth. But the implications were that could be a nuclear bomb, that the Soviets now had the ability to drop a nuclear weapon anywhere on Earth that they wanted to. And that was very scary. And so the Americans had to demonstrate that they could do the same thing. And so you can sort of imagine there's like, on the one hand, you've got this, they're trying to show that they can put a human on the moon. They're trying to show they can put a human in space. Like, that is a demonstration of the technological and financial might of a nation. But we saw what happened, right? Once the Apollo mission put the first human on the moon, then you no longer had any people going to the moon for 50 years. And so mission accomplished, but that should have been the beginning of a long future in space. Watch the TV show For All Mankind. That's how it should have played out. And yet it didn't. And so I think that there are better fuels, better motivations, like just scientific inquiry about attempting to explore, right? There's a race to be the first person to climb Mount Everest, but there's also real value in just exploring every nook and cranny of the Earth and the solar system. And over time, those accrue greater benefits than what you get just from a competition. And so I am always really uneasy by by people hoping that there's going to ignite a new space race, that China sending off their Mars sample return mission in 2028, and then them potentially having humans land on the moon by 2030, people hoping that's going to encourage and inspire other nations to move faster. And I think that's unwise, right? And in fact, I think collaborations across the nations. And I think that landing humans on Mars, for example, is going to be such an expensive, such a complicated process that you really need a lot of different nations working together, like you had with the International Space Station. And so I think there's a place for competition, healthy competition, and there's a place for cooperation. And I think both should come together. Ideally, you're cooperating while you are competing in some way. I'm not sure how that plays out, but yeah, I feel a little anxious when people are hoping that by China setting foot on the moon next, it will be an encouragement to invest more money in spaceflight, because that's not the greatest way that's not the best reason to invest in spaceflight. It's the other benefits that you really want to accrue. But, I'm a big fan of the free market and capitalism. And so I think that having a lot of players all at the same time has tremendous benefit as well. And so I'd like to see that too. Jay Steiger. I was thinking in the shower this morning while listening to a podcast, what is the speed limit that can be achieved by slingshotting around planets? So gravitational slingshot is what's used to accelerate spacecraft here in the solar system. You take advantage of the gravity, really of the orbital momentum of a planet as you go past. And so, when you think about, say, a spacecraft that's going to fly towards Jupiter. So like imagine you've got a hill that goes down that comes back up again. And so your spacecraft is going to fall down this gravity well as it approaches Jupiter, and then it's going to decelerate as it's coming up the other side of the gravity well. And they actually they balance out. But at the same time, your spacecraft has been pulled up to Jupiter's orbit. And so you get to gain the speed that Jupiter is going around the sun. You also slow down Jupiter a tiny little bit, but Jupiter doesn't care. It's got lots of mass. It's not going to spiral into the sun anytime soon. And so you could do multiple versions of those. Like when the JUICE mission flew past the Earth and the Moon, it got a 0.5 kilometer per second speed boost by going past the Moon. And then it got a 4.5 kilometer per second speed boost going past the Earth. And so it got a 5 kilometer per second speed boost going past the two of them together. And so you could do multiple planets. You go past Jupiter, you get a speed boost, go past Saturn, get a speed boost, go past Neptune, go past Uranus. And in fact, that's what the Voyager spacecraft did. Voyager 2 went past all 4 planets, getting speed boosts from each one of them, and is now, way out in the outer solar system. And so the practical limit is when you're going to run out of planets that you can conceivably do slingshots past before you are slung shot out of the solar system. And the escape velocity of the solar system from the Earth is about 16 kilometers per second. And so if you add 16 kilometers per second as you do a slingshot past the Earth, you're now on an escape trajectory. You're never going to come back into the solar system and be able to do another slingshot. But if you could aim things perfectly, you could go past, say, a nearby brown dwarf, and you could get a slingshot, a speed boost. You're going to steal some of its orbital momentum around the center of the Milky Way. And the most ideal object that you could do a slingshot by is a black hole. That if you could just skim the event horizon of a black hole, you get a massive speed boost. And if you could sort of dial things in, you could go past multiple black holes, and you could seriously approach relativistic speeds, get closer and closer to the speed of light. And you can imagine that is a method that advanced civilizations use to send spacecraft out into the larger universe at close to the speed of light. They know the positions of all of the black holes in the Milky Way or in their home galaxy, and they line them all up, and they've worked out their perfect grand tour past all of those black holes, coming just close enough so your spacecraft isn't torn apart by the tidal forces as it goes past that black hole, and then onto the next one, and onto the next one. It just speeds up and speeds up. You get relativistic speeds, and the price you pay is the black holes are slowed down a little bit in their orbits, and they orbit a little closer to the center of the Milky Way. It's not a big deal. So yeah, you just need to know the exact positions and motions of those black holes, and you could go close to the speed of light with your spacecraft. All right, those are all the questions that we had this week. Thank everyone who asked your questions in the YouTube comments, as well as everybody who joined me for the live show. Now, we record this show live every Monday at 5 p.m. Pacific. It's 2 hours long. There's the first hour that we turn into the question show, and then there's a second hour that we call overtime, and it is secret. It's hidden, and yet you can access it. We put a link to every episode over on our Patreon, completely free. So if you go to patreon.com/universe today, you follow us on Patreon for free, you'll get a link to the full episode there, and no ads on everything that we do. So you should definitely come and check that out. I want to ask you a question, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew M. Gross, Barry Lake Roofing, David Gilton, David Matz, Dennis Alberti, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Paul Rohrbox, SpiderSwap.io, Stephen Krasaki, Stephen Fowler Munley, and Vlad Chiplin, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. So when you're watching this, we posted a new interview where I looked into astroseismology and did an interview with a researcher. And this was based on the audience, you, telling me that this was a topic that you were really fascinated about. I had sort of mentioned casually offhand in another interview that there'd been this revolution in astroseismology, and it gave us precise ages of stars in a way that was never really accessible before then. And it was all thanks to the latest planet hunters and this entirely new field, and people wanted to know more about it. And so I found a researcher and I got their questions answered, and it was great. It was really wonderful. And so I think, a lot of the times I'm really focused on the stuff that I'm most curious about, but I think, there's a lot of topics that I would love to I feel like I'm the bridge between you, the audience, and the scientists, the researchers. And I'm able to reach out and actually talk to them and ask those questions. And I know the questions you want to ask people, but I would really love to know who you want to talk to. So now, when I ask this question in the past, what I often get is specific people. And so I don't want recommendations for people to talk to, because in general, I tend to avoid celebrities and very well-known people. And instead I look for people who are just, they don't have a social media presence. They're well-known to other astronomers, but they're not really that well-known to the public. And so in the comments down below this, just put a topic or something in space and astronomy that you are curious about and you'd like to know more about, that you feel like there's a lot of missing parts in your knowledge and understanding of it. And then I'll look through that list, and then I'll find some topics, and I will reach out to some researchers, and I'll try and queue up some interviews so that I can get your questions answered. And if there's if you see somebody else has done a really nice description of a topic, then thumbs up them. And then I'll see the ones that have a lot of votes, they'll rise to the top, and I'll be able to sort of consider that as a way to do additional priority. So, I can't promise I'll be able to get to the bottom of any of these, but it's a way to sort of know really what you want to hear. So let me know.